Hello everyone, welcome to my structural analysis tutorial section. Today I'm going to talk about how can we draw bending moment effectively. Uh, First of all, let's have a small recap. Suppose that I have a beam, horizontal beam, and then let's say I cut a point. Okay, let me remind you that if I cut this point, we have let me make it separate it more. Okay, you will find a pair of axial forces. Okay, and then shear force and a pair of bending moment. All right, and we call this kind of bending moment positive. Okay, when it pulls the bottom side. When I draw the bending moment like this, right? You can draw the bending moment like this. It means that the face. This is the face of the beam, right? The bottom part, the bottom part is under tension. Okay, so when the bottom part is under tension due to this bending moment, we call this moment positive bending moment. All right. First of all, how can we draw bending moment effectively? All right. Um, Let me show you the derivation first. Some basic principle. Suppose that I have a beam here. If I have a let's say uh, clockwise bending moment, concentrated external moment acting on this point. Let's call it M0. All right. Let's say I want to investigate the moment at the left and the moment at the right. Okay, let's call this M minus, and I say MA. Let's call this point A, and let's call this point B. Okay, what's the relationship between MA and MB? Right? What's the change? Okay, in this very small distance. If you cut this segment out, you will find something like this. This infinitesimal small. Okay, there is a concentrated moment. External moment we call it M naught. Let's assume that the bending moment at point A is positive. It's something like this. Okay, MA, because this is at the right face of the beam, right? The right face of the beam. Okay, when I call it positive, it means that it is how to say clockwise. Okay, and this is the left face. Okay, this is MB. From moment equilibrium, okay, we know that MB should be equals to MA plus M0. Okay, so the change of moment is M0. What means that if you see a clockwise, okay, bending moment, okay, the change of bending moment from this point to this point is positive of this magnitude. How do you remember this? You can treat this bending moment, okay, because this is and this is clockwise, right? How do we think of this, whether this is positive or negative? First of all, the magnitude is let's say 50. Okay, when we think of the changes, right? Whether we should think of it positive change or negative change, it depends on the direction. We can think like, okay, this moment is acting on the right face of the beam. Okay, you can imagine like this. Okay, so this is a positive moment. So we gain positive moment if this is clockwise. Okay, later we will do an example to illustrate this clearly. Next, okay, next. Suppose that, okay, I have a beam, and then we have some distributed loads. Okay, for convention, let's assume that the distributed load is pole is upward. Okay, and then let's call it omega x. Okay, let's say x is measured from here. Let's say I cut a small pieces out. Okay, very small. Let's call this dx. Okay, and this is the segment, and then we have some external load, okay, W or Wx, because this is a very small, so we can assume that this is like a constant, okay, approximately. And this is we have a shear force, okay. Let's assume that the shear force is positive. This shear force is called V of x, because E is the position x, okay. And then the shear force here, let's say this is called V of x plus dx. Let me remind you, the distance here is dx. Of course, we have axial force, of course this doesn't matter, it will not affect the movement and also shear force. And then we have moment, in this case, this is moment. The moment here is called m of x, and this is called m of x plus dx. Alright? Let's say I take this point, okay, as moment, let's call this point O. Okay, summation of moment at point O must be 0 because this is a static system. So for moment equilibrium, we know that, okay, this is m x plus dx is a positive because it's anti-clockwise, and then minus m of x is clockwise, and then minus, okay, minus d of x times dx, the distance is dx. This force does not create moment because I take this point, and then also minus the moment, okay, omega x, because it's infinitesimal small, so we can assume that it's a constant, okay, times the distance is the magnitude times the centroidal distance dx times 2 equal to 0. Alright, we can see that, okay, this is dx, this is dx times dx, this is one order smaller than this, okay. It's like this is 0, okay, this is 0. We can choose sufficiently small of dx such that this value is negligible. So from this equation, after you rearrange it, you will find that v of x is equal to m of x plus dx minus mx divided by dx. Okay, when dx approach to 0, okay, when dx when then this is like a derivative, right? So v of x is actually the derivative of bending moment. So this is very good, very important implication, okay. When you want to know the slope of bending moment is equal to the shear force at that point, at the continuous point, okay. So in other words, the bending moment, okay, let's say we integrate both sides of dx, right? So between 2 points, okay, is simply let me erase this first. Is simply is simply the integration between 2 points, okay, and then the area under the shear force diagram. All right, let's have an example. This is very important. This equation is very important, okay. The changes of two of 2 points of the bending moment, okay, depends on the shear force diagram, okay. So what I mean is that in order to draw bending moment, you need to have you need to draw the shear force diagram first. Of course, for some simple cases, you can directly draw the bending moment, but in general, you need to draw the shear force diagram first, okay. Let's do an example. Let's randomly draw something. Let's see. Let's say I have a beam like this, okay, and then I have a column like this, okay. I have a roller support here, and then I have a pin support here. Alright. Let's say I have a force, concentrated force here, 60 kilonewton. Okay, all the units are compatible. Let's don't care about the unit first, and then we have a concentrate, we have a distributed force acting to the left, and let's say the intensity is 10, okay, kilonewton per meter. Okay, let's give some dimension, it doesn't matter, okay. I randomly give you some number. Let's say this is 2, this is 4, and then 2 meter and 4 meter, okay. This is 4 meter, okay, this is kilometer. Alright, the first thing we need to do, okay, for this particular question is to find out the reaction force. Alright, let me show you. Let's quickly go through it, okay. This is, let's skip this point A, B, C, and then this D. Okay, we have a pair of reaction force here. Then we have another output here. It's called dy, and then this is a, y, and then ax. Okay, from the force equilibrium, we know that ax is equal to 10 times 4 is 40. Alright, if this is from summation of the force along x direction. If I take the moment at point A, we know that, okay, dy times 4 minus 60 times 6, the bending moment generated by this concentrated force here, okay, and also minus, okay, the bending moment created by this distributed force, which is equal to, this is 40, right? So this is 2, okay, this 36, the moment arm is 2, so it's 40 times 2, so 0. From here we know that dy is actually equals to, let me take out my calculator, 60 times 6 plus 40 times 2 divided by 4 is 110. Okay, 110. Sure, needed. Alright, so from summation fy equals 0, we know that ay plus dy minus 60 is equal to 0. So ay is negative 50 kilonewton. Okay, we can start to draw our shear force diagram first. Okay, so ay is negative 50, so it means that the shear force diagram is something like this. Negative 50. And then because there is no distributed force or any forces in between AB, so the shear force remain unchanged, okay, remain unchanged. And then after this point, okay, okay, if I cut this point, right, we know that, okay, this dy will push the shear force upward by 110. So this is here at the right side of point B, the bending moment, the shear force is positive 60. Okay, and then at this point is pushed down. Okay, so the shear force beam ABC something like this. For this let's call this x1, and then this is x2. Okay, and then let's call this x3. Okay, let's call this x3. And then okay, this is 10. Okay, so we knew that, okay, the shear force at this point is 0. Okay, the shear force at this point is 0, and so the force is something like this with the slope of 10. Okay, so this is the 40, right? So let's quickly go through the shear force, the equation to describe this shear force diagram is negative 50. V of x2 is 60. V of x3 is the starting point is 0, and then plus, what's this? The slope is 10. Okay. Right. And then bending moment. Let's start to draw the bending moment. let me remind you, when we draw bending moment in civil engineering, okay, we plot at the tensile side, okay, we plot at the tensile side, okay, tensile side. So for this bending moment, okay, something like this, okay, it's negative, okay, tensile at the top, negative 50 times 4 is 2, I think it's 200, yeah, it's 200, negative 200. And then for this one, okay, for this one, okay, for this point, okay, this point, the bending moment is should be, okay, cut this point, okay, is 60 times to 100, this is something like this, okay, negative 120, and then somewhere around here, and then decrease with a slope of 60. And for this one, okay, for this one, the bending moment is let's see, okay, something like this, okay, because the slope at the beginning of the shear force is 0, so the slope, remember that, okay, the slope of the bending moment is equal to the shear force, okay, so the shear force is so the slope here is very small, okay, so like this, okay, and then after, at this point, the slope is larger and larger and larger. So what is the value here? This is a quadratic equation. The value here is the area under the shear force diagram, basically from this equation, okay, because m1, you can treat the moment at point D at 1, okay, is 0, right? So if I want to know the moment at point B, okay, from this segment BD, then just the area under the shear force diagram is basically 140 times 2, 40 times 4, sorry, divided by 2. Okay, it's 80. Okay, positive 80. How do we know whether we plot the bending moment diagram correctly or not? It's pretty simple. You cut this joint, okay, this is the joint B. Okay, we know that, okay, this bending moment is, the bending is at the top, so the moment is something like this, 200. For this, for the right side, okay, the moment is something like this, 120. And for this column, okay, for this column, the moment is at the right side, so it's something like this, okay. Okay, so it's balanced, okay, so it means that we draw the bending moment correctly. Let's write down the equation. The equation is mx1. Okay, mx1 is the integration of vx1, basically is negative 50 x1 mx2. Okay, the starting point is negative 120. Okay, the starting point, okay, of point B, and for segment BC, okay, and then we integrate the function of vx2 is nothing but 60 x2 and mx3. The starting value is 0 because at point D the moment is 0, and then we integrate the moment for this segment. Okay, basically it's 5x3 squared. Right. Thank you for watching, and if you like my video, please subscribe me, and